All right, well, thank you, everybody. So, should I just go ahead and start the time? Oh, okay. So I was fine up until this point, and then I saw that my entire qualifying exam committee is in the crowd. So this is taking me back to when I was getting ready for quals. But today, I just want to talk a little bit about some of the work that we've been doing, trying to get a handle on aerosol in the Southeast U.S. And before I begin, I just want to thank all of our co-authors here. The list grows, but I think we really need to thank the SEAC⁴ science team in general, because without them, we met them in Houston last summer, and none of this would have been possible without the data. And so I think what I'm talking about today is going to mirror a lot of what Dan Murphy talked about, and I think we're converging on the same story, but with different methods. And so just to get you a little bit oriented here, when I'm talking about the Southeast U.S., I'm really just talking about this black box here of 7 states and some change. And as you can imagine, we're focusing on the summer, where it's the seasonal max in surface PM 2.5. And so what I'm showing you here in the circles are the summertime averages measured at the EPA AQS sites. And the background is what we simulate with a 25-kilometer resolution version of the GEOS-Chem chemical transport model. And so what you'll see is in this black box, you see this red blob here that's characterized by high temperatures, high relative humidities, and frequent stagnation events. And so this point has already been made, but this red blob is changing, and it's changing fairly rapidly. So I've just broken apart the different aerosol components, and what you'll notice is that over for summertime averages over the past 10 years, and what you'll notice is that the inorganic components, in particular sulfate and ammonium, have dropped by a factor of 3 over this time period, and this is shown in these trends that I've calculated for you here on the right. And in contrast, organic carbon hasn't dropped nearly as fast. And so this trend and this star actually means that the Mann-Kendall statistic is basically on the verge of significance. And so what this means is that the relative importance or the relative magnitude of the different aerosol sources is changing with time. And so we'll need to understand that in order to understand what our mitigation strategies of tomorrow should be. And to add a little bit more further intrigue to our story, this is actually a question that was first posed by the first speaker in this session. And what Alan noticed is that if you take a look at the available satellite aerosol optical depth products, you'll see a very strong seasonal cycle with a very strong regularity here, with a peak in the summer and a minimum in the winter. If you take a look at the surface station data, you'll notice the same type of seasonal cycle with a summertime max, and it's mainly driven by ammonium sulfate and organic aerosol. But the question is, why is there such a large difference in the magnitude of the seasonal cycle when you look at the surface station data compared to the satellite data? It's more like a factor of 4 when you look at the satellite data versus a factor of 1.5 in the surface aerosol concentration. And so the prevailing hypothesis has been that this is due to an elevated layer or elevated source of organic aerosol aloft. And that's decoupled from the surface, so you're not necessarily seeing it in the surface station data, but you're picking it up in the satellite aerosol product. And so that's going to be very important if we're trying to use that satellite aerosol optical depth in order to map surface air quality. And so coming at it from a different angle here, so Dan Murphy showed a calculation looking at the SIPC improved site earlier this morning. Here I'm looking at a more regional perspective. So if you take, for example, all of the EPA surface PM 2.5 in the Southeast US, assume in a very simple calculation that that's lifted up and distributed evenly throughout the depth of the boundary layer and apply some mass extinction efficiency, then you can pull out a factor of 2 seasonal cycle in the aerosol optical depth that you measure or that you estimate from what's in the surface layer. And so that's actually what we see from MODIS for 2013, and this has the added bonus where you can look back over the past 10 years and you'll see that from 2005 to 2008 it's more like a factor of 4, and as the aerosol loading decreases with time, that seasonal cycle also decreases with time in the estimated aerosol optical depth. And so it seems here that the planetary boundary layer height is the missing link between the surface and what we're seeing in the column, and we don't necessarily need to invoke an aerosol layer that's lofted in the free troposphere. But there are still several questions that remain. And so these are what I'm going to focus on for the remainder of this talk. In particular, what are the sources of aerosol in the Southeast US? I mean, we still don't really have a handle on that. And how are they driving that seasonal cycle that we're seeing both at the surface and in the satellite aerosol optical depth products? And finally, what will be the implications for when we're trying to use these aerosol optical depth products to map surface air quality? And so our approach here is shown here in this diagram, where we're going to use the surface station data and the satellite data for which we have a fairly good record at this point. But we're going to supplement it with data from the NASA SEAC⁴ aircraft campaign, which I'll chat about in just the next slide. But at the middle and at the heart of all this is the GEOS-Chem model, which we're going to use as a transfer platform. So in the simplest sense, the model is self-consistent with itself. That was, okay, sorry. So we can use it to check for consistency across all the different data streams. And the idea here is that we can use the model to interpret the observations in terms of what they can tell us about the different questions that we're trying to ask. Okay, time is going much faster than I thought. Okay, so just to briefly introduce the SEAC⁴ aircraft campaign and what I want you to take away from it. We were based out of Houston last summer, and this is just showing the aircraft tracks over the Southeast US and the coverage that we got throughout the Southeast US in the gray. And overplot on top of that in the circles is the AMS organic aerosol data below a kilometer. And for the purposes of this talk, what I want you to know about SEAC⁴ is that there was extensive vertical profiling. We had complete aerosol characterization, so more like what you might see at the surface. And then we also had remote sensing measurements, so more like the aerosol optical depth retrieval that you might get from MODIS or MISR. And so really the aircraft data is the bridging gap between the surface measurements and the satellite data that we can use to really attack these questions. Okay, so for this talk, I'm going to start at the surface, and then I want to work my way up through the atmospheric column. And so I want to put 2013 first into context by looking at the seasonal cycle at the EPA AQS sites for the past 8 years. And so there are a couple of things I want you to take away from this. And first, you'll notice that the top row and the bottom row are actually on different scales. And it really accentuates the fact that the summertime max has decreased over time according to those trends that I showed you earlier. The second is that at the surface, the summertime max, the summer-winter difference is really more characterized by a summer-to-fall transition in all years. Even in 2013, I can't even reach, 2013, where the summertime max has really declined dramatically. And the third thing is that we can describe the seasonal transition, at least at the surface, by organic aerosol and sulfate, which we actually saw earlier from that hand paper that I showed you. And so when we start to look at the aircraft data, so on the left, these are showing the profiles and speciation measured on board the DC-8. And so I want to thank the AMS, the SAGA, the PALMS, and the SP2 teams for allowing us to use this data. And so on the left is what we saw on board the DC-8. On the right is what we simulate with the chemical transport model when we sample at the times and locations of the aircraft. And so the first thing to note is just that GEOS-Chem passes the eye test. We're not grossly overestimating or getting the shape of the profile wrong. At the surface, we can show consistency between the aircraft data below a kilometer, the GEOS-Chem model, and the EPA AQS data, and it's telling us that most of the aerosol is organic in nature. And moreover, we're capturing the vertical profile, and from what we can tell, we don't, with the exception of fire events that we saw above 4 or 5 kilometers, we don't really see a lofted organic aerosol layer that could explain a discrepancy between what we see at the surface and what we see from space. And so this is actually kind of hard to see in the aggregate profiles. So I actually want to point you to a poster by Nick Wagner and some of the folks over at NOAA, where I think they've done a really careful analysis looking at it from a profile by profile level to show that there's really not that much of an enhancement and extension in the transition layer between the boundary layer and the free troposphere. And so for the remainder of this talk, I actually want to focus on our approach, trying to use the model to understand what's driving organic aerosol and sulfate in the Southeast US. And so breaking it apart first on the right, so in black you'll see the profile measured by the AMS, and then the gray dots are actually the individual measurements. And red is what we simulate with the GEOS-Chem chemical transport model. And in the dotted lines here are the components that we simulate with the model. And so here we're actually using an extension of a simple parameterization by Hodzik and Jimenez 2011. And so there was discussions earlier this morning about how much complexity we need in simulating organic aerosol. And here, for our purposes, we were actually able to capture much of the variability. An R of 0.85 means that we were capturing about 75% of the variability in the data. And what that parameterization was actually telling us is that most of the organic aerosol, at least from SEAC⁴rs, was secondary in nature, and it was coming from isoprene. The nature of these slides is this was 5 months of work, and I'm just giving you the overview. But the most interesting thing about sulfate on the left is that with our conventional understanding of sulfate oxidation from gas phase oxidation by the hydroxyl radical or aqueous phase oxidation by hydrogen peroxide or ozone, we were not able to explain the sulfate burden in the Southeast US. We had to include Kriege intermediate chemistry in order to, especially at the surface, capture the observations in the data. And so by Kriege intermediate chemistry, I just mean this line right here. They're formed by the ozonolysis of terminal alkenes, so here it's mostly isoprene. That can then form these stabilized Kriege intermediates that can react with SO2 to form sulfate. And so this is interesting and is gaining some traction in the literature in the past several years because this is a biogenic or natural emission or interaction with anthropogenic pollution that's leading to the formation of aerosol in the Southeast US. Okay, so we've taken a look at the surface data, we've taken a look at the aircraft data, and we think we have a better handle on trying to understand what's driving the aerosol, at least in terms of the chemical composition in the Southeast US. And so I mentioned earlier that we had looked at MODIS and we'd seen about a factor of 2 in the seasonal cycle between the summer and the winter. And so we want to understand what's driving that seasonal cycle. Fortunately, SEAC⁴ rs was situated right in this window where we start seeing the seasonal transition from summer to fall AODs. And so we have some confidence in our model to be able to understand what's driving the seasonal transition. And so if we just zoom in on this window here, so in black, it's the summer average over the Southeast US. Actually the daily averages, I'm sorry. And then red is what we simulate with the GEOS-Chem model and then broken down by components are the contributions from organic aerosol and sulfate. And so what you'll notice is that even though the sulfate levels are less than organic aerosol, it still dominates in the aerosol optical depth. And the model tends to underestimate the aerosol optical depth in general, but I think we have some ideas and avenues to explore around why that is. But it captures the variability. And so what it's telling us is that the seasonal transition, at least in the satellite space, is driven by a combination of 2 factors. And the first is that there's a shutdown in the natural emissions with cooler temperatures. So think less isoprene, less formation of SOA precursors. As I showed you earlier, isoprene also bleeds over into sulfate because through the Kriege intermediates. Sulfate actually has, in the second part, a second contribution from the shutdown in SO2 oxidation. So as the seasonal transition occurs, you're getting less UVB, and so you're forming less HOX. And because of HOX competition for NOx, you're shutting down hydrogen peroxide production as well. And so what we're getting here, though, is a consistent picture between the surface data, the satellite data, and the aircraft data. And it's telling us that this extinction and this seasonal transition can be explained by what's going on in the boundary layer. Okay, so I have 2 minutes left. So I'm just going to throw up these conclusions here. And so in the remaining time that I have left, I just want to advertise this talk and this poster that are on Friday. I didn't get a chance to talk about the importance of fires in the Southeast US, but I think these 2 you should really go to. So with that, thank you for your time, and take any questions. Sure, no, and that's a great point. And we do think that there is some underestimate in our hydrogen peroxide production. But even if we were to double our hydrogen peroxide production, we would not be able to match the sulfate burdens in the Southeast US. So we think there is, if not the Kriege intermediates, something that has the same spatial temporal location at the surface that matches Kriege production. So that's an excellent point. And so I didn't show it on this slide here, but we've looked at the profiles of sulfate production. And so our idea first was that we weren't making enough sulfate through hydrogen peroxide oxidation in clouds. But that actually is, the production for hydrogen peroxide is below that bias that we see here. And so we're wondering whether or not it's insufficient vertical mixing in GEOS-FP, but that's something that we haven't really explored yet.